next time we should shift from recitations to hackathon day.
Maybe, yeah, because it's at a normal time.
It's at least 30, 40
I'll be there regardless. Yeah.
Like, we expect this, but kind of like homework first, time, right? Not like homework through the
Well, I'll tell you what, just cancel today. We'll just crowd around and do my homework. And then we'll just do this tomorrow. Sounds like a perfect plan to me. I think there was some confusion because of Peach's announcement.
Good, sorry, confusion what? Oh,
Because we weren't having class on Wednesday and Monday, so Friday got looped into all that.
should we wait for like 5 minutes to see if anyone is coming?
Because we're not, except for shortens, we're not really holding anyone. Even on Zoom, it's happening.
Okay.
Just to let you guys know, you do have like 8 people on Zoom, so I don't know if that's worth
Okay.
it or not, but.
Yeah, we just wait for 5 more minutes.
Okay.
Thank you. Okay, so the agenda for today was to sort of take you to the fine-tuning part of the homework, because access has been started notebook and completing. So just how to integrate it with the main notebook and how to finish that code.
Oh, yeah.
Because maybe we should have announced it, but okay, we at least have post after the recitation.
But I haven't even, like, I got the low cutoff for the part 2. I didn't even implement the,
Yeah, you don't need to. Yeah. You need it for the high cutoff for verification.
okay.
The rest is not. Sometimes you may not even need it, but it's good to know.
Yeah.
It's just been 1.5 months. Yeah, that's about 18
Yeah. So today we'll talk about face classification and verification. I'll start with the classification part, and then Ishan will take over for verification. So what is classification? So our goal is to predict the number of classes. My apologies. So our goal is to predict the class label for any given input image. And because we have multiple classes, this is a multi-classification problem, and you'll have roughly 7,000 different people, and we want to predict which image is of which person. So each person becomes a class here. Now, the classification can be done on closed set or open set, and similarly the verification problem, which we'll talk about, which is actually using open set for us. So the difference between closed and open set is that in closed set, our labels or the classes in training and test data are the same. So we might have a different image of the same person in test, but the person will still be same. The person will be present in the training data as well. So here we only have to find decision boundaries among which separate our classes. However, in the open set, we can even have new people in test which are not present in training, which means your model should be able to generalize to a completely different person altogether and tell if which images of the new person is belonging to the same person versus which of the images probably belong to the people who were part of the training set. So in open set, instead of finding decision boundaries, we try to cluster all the samples together. So our final example, our final state looks more like for every individual that we are aware of in the training data, it's part of a very close boundary, versus anyone who is outside those boundaries are unknown. But for verification, even people outside the boundary, their images will all be lying close to each other. So even for two unknown people, we should be able to tell which picture belongs to which person. So in our homework, the classification will be a closed set problem, but with verification, you'll have a lot more new people in the test set which do not belong in training. And this is how even your face verification would work for your iPhone or your laptops, is that the person who, the engineer who trained that face verification software did not have access to your picture because he or she did not know which person will be using the iPhone. But once you show the device one or two samples of a picture, they're able to figure out whenever you are logging in versus someone else is logging in. So that's the advantage of having verification on OpenSet, that you can very easily customize that model to work with any new person. So yeah, this is a pictorial example of the closed and open set, and the difference primarily here is that the identities, the people in the test set are same with training for closed, and we'll have new identities in the test set for an open set problem. So this is how your pipeline model will look like for the face classification problem. We'll use multiple convolution layers, etc., to extract features from a person, which we are calling feature embedding. So for the same person, the feature embeddings should have a high similarity. But for different people, the feature embeddings should have a low similarity. And then we pass it through, for the classification problem, we pass it through a linear layer and get the probability of each class. So, and yeah. So now with the pictures, one of the problem is that picture of the same person can be taken in multiple backgrounds, multiple lighting conditions, at multiple angles, etc. So, but the convolutions are not rotation invariant. So by default, the convolution network cannot really tell if it's the same person, if it's rotated by some angle. So to make the entire architecture more robust to these invariations, we try to augment our training data. So this just allows us to make sure that our model is learning to find the person specifically, not the background that they were in, or not focus on what kind of lighting conditions they were in, or what angle was it in. So this was covered in more detail in the bootcamp, so I won't go in depth here. But even though the early cutoff does not require any augmentation, you can very easily reach early cutoff for homework part 2 without augmentations. For reaching high cutoff, your model will have to become more robust to these variations, because the test data will have much more variations for the same person's picture than the training data. Now, when you train deeper networks, one of the problems that we face is that of vanishing gradient or exploding gradient. Is as we go deeper into the network, our gradients become either way too large or they just become close to zero, which makes the entire training impossible. So empirically, what people found was that if you add this residual connection, if you add the input being fed into any of the layers to the output of a few layers down the line, you can actually solve this problem. So people did this empirically. Should you add residual connection by skipping 2 layers, 3 layers, 4 layers, 5 layers? And found that the 2-layer gives the best result. And so this is how the residual connection came into picture. If you look at the later papers, they even go into, from a theoretical standpoint, they go into the depth of why 2 works. But most of these blocks, or most of these architecture designs are achieved by having a lot of empirical testing around, and then you find which ones are working better. So similarly, when you're designing the blocks for yourself, or when you're designing the architecture for your own homework, you should also experiment these variations. But just for the sake of residual connection, it will be usually 2 blocks or 2 or 3 layers skipped by the connection. So let's come to the resonate block, which was introduced in the paper when they also talked about the residual connection. Is you have 2 layers, which are simple convolution networks, and then you're adding the input of the first layer to the output of the second layer. And to make this addition possible, the dimensions, the channels of these input of first layer should be equal to the output of second layer. So hence, in this setup, they're not changing the number of channels throughout these connections. So if you have to downsample, you'll do it probably after the 2 layers altogether, but not in between. So this is how it would look like. So in this example, you see there's a 64-dimension input, which goes to a convolution layer, which has a 3 kernel. The dimension remains unchanged. So there is a mixing happening between the spatial dimension and the channels, but overall we are not changing the number of channels in this setup. And that's the reason we are able to add the input going into the first layer to the output. Now, this was another block which is proposed in the same paper. So the one we saw previously was the basic block. And what people found was, as you go deeper, the number of parameters increase largely, even with the residual connection and a basic block. So how can we reduce the number of parameters to make the training easier for much more deeper networks? And this is where they used something called a point-wise convolution. So in a normal convolution, you are comparing, you are mixing the data pixel values in the spatial resolution with the number of channels. But in point-wise convolution, you have a kernel of 1 cross 1. So you're not mixing data from 2 different pixels next to each other, because each kernel is only focusing on 1 pixel at a time. But your channels is getting mixed. So the advantage of point-wise convolution is that you manipulate the channel values without really changing the spatial dimension. So yeah, so they use 2 point-wise convolution. The first one will downsample it, and so from 256 dimension, it will bring it down to 64 dimension. And sorry, not downsample, it will be upsample. So it will, from 256 dimension, it will bring to 64. Then you will do a regular convolution on the 64 channels, and then again you bring it back to 256. Hence, you're able to add these 2. And the advantage of point-wise convolution is that you are able to share parameters. So the more parameters you are able to share, the less number of parameters you need in the convolution, which makes it more efficient. So this is how, for a comparison, the basic and the bottleneck block will look like. So if your architecture is shallow enough, basic blocks would be good. But as you go deeper and deeper, you might have to start exploring the bottleneck blocks in the system. So this will be your overall architecture. You'll have a stem, which is basically a simple convolution with some normalization and pooling. And then you work with the stages. So each stage will have multiple blocks. It can have it can have 2 or 3 basic blocks, or it can have 2 or 3 bottleneck blocks. And then finally, you reach the feature classification layer. So yeah, this is how the architecture will look like. So in this scenario, on the left-hand side, the second column, it's capturing the spatial dimension. So you see it started at a 1112 by 1112, and it reduces down to the 1 cross 1. So in the 1 cross 1, now you can actually make this a simple batch, comma, number of channels, which can be fed into a linear layer. And you would see that because you are adding the input of the of the first channel, first layer into the output of the last layer in the block, you don't really change the number of channels within the block, but you still need to throughout this architecture, you will still be increasing the number of channels and reducing the number of spatial dimension. So finally, you will only have 1 pixel and a lot of channels. So to do this, you will be downsampling throughout this architecture. So every time you downsample, let's say you downsample by 2, you will be increasing the number of channels by 2, and you will be decreasing the spatial resolution by 2. This is the next block, which was inspired by the transformer architectures, which are coming out in the late last decade. And then people were stopped using convolutions altogether, because transformers was like, you can do the entire thing just using attention. So convex used many of those concepts from the transformer paper, but it used only the convolution layers to see how can we make the resonate block give us as close to the results as of a transformer. So the primary difference here was that instead of having like a point-wise convolution, then a regular convolution, then point-wise, you are doing a depth-wise convolution in the beginning. So the difference between point-wise and depth-wise convolutions is in depth-wise, you are actually mixing up the spatial channels. So you're mixing the spatial resolution, the pixels, without while keeping the channel separate. So each channel goes through its own kernel. Versus in point-wise, you are keeping the pixels same, and you are trying to mix up the information across channels. And also they changed a few other things, like they used GELU instead of ReLU activation, and they used layer norms, etc. So you can even look at papers, for example, to see which kind of activations work better with what kind of layers. You can even look at what kind of optimizers will work better with convolution layers. The same optimizers that are giving good results in linear may not give you the best results in convolutions. So many people have done these kind of empirical studies about what kind of activations, what kind of normalization, what kind of optimizers, etc., will work better with which kind of layers. So just a quick caveat here. So even though the convex paper, which was comparing results on the ImageNet dataset, was getting really good results with layer norm, in the current homework dataset, layer norm may not give you the best result. So I would recommend you to explore the batch norm or the instance norms or the other normalizations too. So just don't simply go with whatever the convex provided, because while it was providing good results for the ImageNet, it may not provide you the same results for any other data set also. So yeah, this is just a comparison of the two networks. And yeah. Finally, when you have a lot of classes, you can use something called label smoothing. You can compare. So in a usual classification problem, any kind of class which will have a high probability can cause the network to overfit. So because you have distinct like all the classes are completely separate. So when any class which thinks the model thinks is a huge probability will have like a spike, and everything else will be low. So to make this more generalizable, we try to start to make it a more diffused structure. That's where the label smoothing comes into picture. So if you have many classes, adding label smoothing to your criterion, the loss criterion, can help you have more generalized results. So yeah, you can take over the next one.
Do you want to sort of go over the resonant architecture for 5 minutes?
Sure.
Like just explaining the stems and
Sure.
the differences between anything that would be useful. Because we have to.
Sure. So yeah, in the nested architecture, so the stem is basically just a convolution. So what it does, it will reduce the dimension, and so you will do that initial feature classification with just a convolution, and it will downsample by 4. So it will increase the number of channels by 4, After which you can start going through the each stage. And in each stage, you will have a few blocks. For example, let's say in the 18-layer ResNet, you have two basic blocks. Each block is doing a 3x3 convolution. And then between the blocks, you will have downsampling sometimes. If you in the 34 layer, you will see, so any block here which has 3 convolutions is actually the bottleneck block, and any block which has only 2 convolutions here, which is a basic block. And then the multiply by factor is how many blocks you keep in each layer. And then between the blocks, you can see where you are downsampling. So that by looking at the output channels, you can see where you have to add a downsample to increase the number of channels to go to the next block.
Like, do you guys have any questions about this? Because this architecture and understanding this is sort of important. So just looking at this image, it might feel intimidating. So if there's anything you guys want to know more about
Recording
it,
in progress.
you can just ask. You can continue.
Hi everyone, I'm Arya. So I guess you got to know a lot from Sarthak about the classification task. But like for homework too, we have another task also, that's the verification task. And there might be additional steps that are required um, for you to achieve good results for verification. So I think so far all of you have used cross entropy loss in the homeworks. And cross entropy loss is basically a contrastive loss, and this cross entropy loss gives you a probability value for all classes, right? But for verification, we want to see the similarity between the feature embeddings of the two images we are comparing. And a loss like cross entropy loss does not look at similarity or dissimilarity factors. So we need contrastive losses. Yeah, I suggest you go through the homework 2 part 2 bootcamp if you haven't already, as well as whatever Sarthak just talked about to be able to follow through the next few slides. So like I said, non-contrastive loss functions like cross entropy loss might not be useful, and we need contrastive losses. So what are contrastive losses? These are type of loss functions that are used primarily in tasks that involve learning by comparison, such as similarity learning, metric learning, and some types of supervised or self-supervised learning. The core idea is to ensure that the similar or the positive pairs are grouped together and are brought closer together in the feature space like shown here. And dissimilar or the negative pairs are pushed far apart. So for an example, in the context of similarity, consider two images of the same dog breed, a positive pair, right? And two images where one is of dog and one is of a cat, a negative pair. The model trained on contrastive loss will be able to bring the two dog breeds same in the same space while the dog and the cat far apart. That's the basic idea behind this. So we go with contrastive losses for the verification task. Um, how to train models with such loss functions. So for this part, I will discuss two approaches. Approach one is joint loss optimization. Here, a single model is trained using a combination of two loss functions simultaneously, cross entropy loss and contrastive loss as well. The cross entropy loss is used for face recognition, which is the classification task, while the contrastive loss is used for face verification, which ensures that embeddings or the feature representations of the same person are closer together in the embedding space than those of the different people. And the second approach here is sequential or fine tuning. So basically, in this case, you will first do the classification bit and then verification entirely instead of doing them simultaneously. Like the model will be first trained on for the face recognition using cross entropy laws. And after this initial training, the model is then fine tuned separately using any contrastive loss function. What I mean by contrastive loss function, we'll discuss more later. But so this will be done in two separate steps. And this two-step process allows the model to first learn classify faces and then to refine embeddings for a better verification performance. Um, so let's move to the types of contrastive losses. These are the types of contrastive, some of the types of contrastive losses, which we'll discuss a little bit. I suggest you go back, do your own research about it, read about it, and here are the links also for them if you want to refer to. So moving on to the first loss function, that's center loss. Center loss is one of the most intuitive ones, I think, and it works by minimizing the intra-class variations while keeping the features of different classes separable. It does this by computing the Euclidean distance between the deep features and their corresponding class centers, which are learned during training. So here is the loss function for contrastive loss, and here CYI is the center. So it's the center of this particular groups. It works in a way that it minimizes the distance between the similar pairs and with respect to the center of that cluster, and also make sure to maximize its distance from the other clusters. Um, Moving on to triplet loss. So triplet loss requires sampling three different types of images: an anchor, a positive image, and a negative image. Positive image is as same class as the anchor, and negative image is basically a different class from anchor. The loss function aims to make the distance between the anchor and the positive smaller than the distance between anchor and the negative by a certain margin. It is important to sample in correct way for this particular function. The first thing here is we need to resample. But then we cannot just randomly resample these images, as we need good positive and good negatives for the model to learn, right? For example, let's move on to the next slide that will explain better. Here we have the same image. It's the same person, just in a very different angle. However, this person is different. So I think this makes a very good positive pair, because even though it's the same person, in this particular second image, he is looking away or like in the left direction. So it gives some sort of um, uh, it'll make the model more robust towards learning the anchor and positive pairs. Now, while the anchor and negative might look similar, they're the same angle, the person's smiling, etc., but it's a different person. But it's actually a different person, right? But we also want the model to learn this factor, that even though they look similar, they are different. So resampling in this case and achieving those good pairs for the model to learn is very necessary for this loss function. Um, so one suggestion for all of you in this function is for you to go back and look into how you can achieve this kind of resampling. Um, Yes. So the next one is sphere face loss. This introduces an angular margin between classes to enhance discriminative power of the learn feature. It modifies the softmax loss to use angular distance, which corresponds to geodesic distances on a hypersphere manifold. Now, this might sound complicated, but like earlier you saw that we were using Euclidean distance, right, for the other loss function. Now, for this loss function, we look at the sphere's space and compute cosine similarity between the embeddings. Here in the loss function, theta denotes, just a sec. Yes, sorry. Here in this loss function, theta denotes the type of decision boundary that we want to learn or the parameters we want to train. Uh, and just look at this n here, m here in this in this formula. I'll go to what m is and how it works as a hyperparameter later. But basically, m is the margin for this particular formula. Now, as I said, it deals with a sphere space, which you can see represented here, and here how it changes from when you change the margin from 1 to 4, right? So it can tell you how differentiated you want your points to be as you keep on increasing the value of the margin. So points get much more disjoint when the m value increases, as you can see uh, progressing in these four images. And hence, we would want to tune this parameter whenever we're using this type of a loss function. Moving on to R space. So R space adds an angular margin penalty to the target logits, similar to sphere phase, but it uses an additive angular margin penalty instead of a multiplicative one. These contrastive losses are designed to improve the discriminatory power, basically, of the features extracted by neural networks, which is crucial for tasks like face verification. This is another formula where you can see here we also have a multiplicative angular margin in cos face also. You can go back and look at cos face. We're not discussing that right today. But the additive margin is basically m here. And here, instead of a sphere space, we deal with an arc type of a space when you try to minimize the distances. Um, I, um, yeah, I already discussed this. So if Ishan will be continuing with discussing implementation of one of these loss functions, but if you have more questions about these losses, we can discuss after he walks you through the implementation bit. Thank you.
Sorry. I hope this is visible, guys. Right. So now that we've covered the theory behind these losses, and considering that you all have started your homeworks in the early deadline as well. Sorry. Is it visible? Yeah. Yeah, all right, sorry. Yeah, so now that you all have sort of reached the early deadline stage and you would like to move on towards actually achieving the cutoffs, high cutoff for both tasks, understanding fine tuning as a concept is very essential. You all might have noticed that when we released this homework, we shared 2 starter notebooks in the Piazza post. One is the main pipeline which you all have been using till now, and the second file is called fine tuning starter notebook. I'm not sure if you all have seen it yet, but I would really suggest you to download it now because I'll be walking you through that. And we'll also at the end of this current section be actually doing hands-on, and we'll help you all complete that code a bit so that you can get a head start. So yeah, if you all haven't downloaded, it would be great even for people on Zoom. If you all could just download the fine-tuning starter notebook from the Piazza post for homework too, and we'll sort of continue with that. Yeah, so if anybody on Zoom has any questions about anything we've covered till now, you all can ask that as well, for those who already have the notebooks. Else we'll just wait for a minute so that everybody is on the same page. All right, yeah. Just let me know once you guys are done and we'll continue. All right? Okay. So yeah, till now we've sort of done, like as you can see, this is what your starter notebook looks like. And I'll just scroll through quickly so that you can't really see the code itself, but I mean, you know what it is, right? You'll be familiar with it by this point. Sure. Yeah, but I think you guys have already crossed the very early cut deadline because it was intentionally so, because the things that you will have to do to cross the high cutoff are a little different than what you needed to do till now. The emphasis with the early deadline was so that you all can get a hands-on on how to use CNNs and how to develop conv layers. But as we move towards achieving the high cutoff, you all will have to step out of that zone and look at the implementations of architectures such as ResNet Conf next and learn about how to implement very deep layers, because right now I think we just used a 4-layer CNN, 4 or 5 layer, right? It can be good, you can make it wider, slightly deeper, 10 layers or so, but beyond that, you'd start losing information, and going above 80, 82% would become really challenging. So to achieve the high cutoff, that is where you have to then implement these papers by looking at the papers and implementation of code. And as Sarthak mentioned in the earlier slides, the concept of blocks and stages becomes very useful. Which is why you will have to sort of shift from this very rudimentary architecture to actually understanding, first of all, how to create these complex architectures and how they work as well. Which is why we didn't want you to spend too much time achieving like 75% for early submission and then have to completely pivot to something else, right? But even if you all do implement architectures like ResNet and ConfNext after learning them, achieving a high score on verification is still a little tricky, because as Arya mentioned, the loss that we're using currently is just cross entropy, and it does sort of help you split your output into various classes, but it doesn't necessarily ensure that each of the class is distinct from each other. So the decision boundaries aren't necessarily going to have a margin in itself, they're just going to be probably blurry, right? Because that is not necessarily a factor that we're tuning it for. So what verification relies on is each class being located as far and as uniquely identifiable from the other as possible, for which we use the contrastive losses, as Arya mentioned. So just to start with understanding how to integrate the fine-tuning aspect into your main pipeline, I thought it would be good if we just sort of covered it, right? So in the current notebook that you guys have, after the experiment cell, you just have these headings, right? Fine-tune your model, model definition, and they're blank for you. So what you would have to do is, in a way, from the fine-tuning starter notebook, there are 3 major kinds of contrastive loss-based implementations in arc phase, sphere phase, and center loss. We expect that you guys will sort of distribute tasks amongst your study groups and try to experiment with which one works best for your models and which one works best for your particular set of parameters. And then once you all have concluded on which one works best for you, you then import that model into your main pipeline and then fill in the other cells correspondingly. Because how the other cells are filled depends on the model that you choose. If you use sphere phase or arc phase, they have a similar implementation going forward. But if you decide to use center loss, the implementation for that is a little different. And what it requires in arguments for the optimizer or the criterion and how you actually train is also slightly different, right? So yeah, I'll first take you through the starter notebook now so that you all can get an idea of what all we have in the starter notebook for fine-tuning itself. And then once we cover that, I'll sort of shift back to the main pipeline and show you how to integrate that into the actual notebook itself. So yeah, with the fine-tuning starter notebook, right? Arc phase, sphere phase, and center loss. So coming to arc phase. I'm not sure if you all understood entirely when Arya was mentioning it, because that was just a formula, right? But if you look at code, it sort of becomes a little easier to understand what is happening. If we look at this formula here, that is sort of the loss that arc phase is trying to minimize. And if we see, it is very similar to softmax in how it is represented, right? But the major difference is the exponent power, which is now a factor, which is now dependent on theta and margin both, right? Unlike just for softmax. And if you see, you have this term as an additional bias. Now, how that implements in code is as follows. You have just the initialization. The margin and scalar are the main hyperparameters coming to arc face and sphere face. And you would have to do grid search over these hyperparameters to extract meaningful separation of classes when you do train. So this is something you definitely need to remember, because even if you do implement these correctly here and in your pipeline, if you do not do a good search for these values of hyperparameters for your specific model, you will not see any improvement at all, right? And it is really model specific as well. So something that worked for another study group who is working on a similar, albeit a different model, may not necessarily work for you, right? So it is highly recommended that you must do a grid search over these hyperparameters after implementing it to find what works best for your model. Although it's straightforward, you shouldn't need more than 5 to 10 epochs to figure out, at least relatively speaking, which value of margin or scalar works for you. Right. And then, yeah, so we have init and then we have forward, right? So in forward, basically, yeah, okay. So init, what we see, the initial arguments are model, margin, scalar, embedding size, num classes. Model is the model from the classification stage, the model that you've already trained for how many ever epochs for your classification, and you have achieved a good enough value for your accuracies, right? We directly import that model with its learned weights into arcface. We provide these arguments of margin and scalar. The default values may not necessarily work as they usually do for the starter notebook, so you feel free to sort of understand what ranges of values are expected. For example, margin is usually much smaller. You can experiment with starting from 0.1 all the way up to 5 with like significant steps in the values that you check, and narrow it down as you keep progressing. So you can start with 0.1, 0.5, 1, 4, and then see which range works best, narrow it down, and then maybe check 0.1, 0.3, 0.5, or 1, 1.52, whichever works for you. And if you look at scalar values are much higher. You could start experimenting with something from 32, 64, 150, 300, and then narrow your search down as well. Embedding size is dependent on the last layer, the embedding size depends on the last layer of your model itself before we pass it through the linear layer. And num classes is the number of classes that we are trying to create. So in forward, another major difference is, unlike a regular model where we only input the images, we are also going to input the labels, right? So this is separate, and you can't really use the same forward for training and inference, right? This is significant because usually our model doesn't take in the ground truth at all. That is just something that the loss handles, right? And why do we need the labels? We need the labels so that we can actually calculate the intra-label, intra-class separation and ensure that the classes are as separated as possible and easily identifiable. So if you see, there is only one modification in which we have these parameters that are being learned, but the loss itself is being calculated differently, as Arya mentioned, using theta and a margin. So we'll sort of come back to this when you guys can do a practical hands-on after this. But these are the sections that you sort of fill in, right? Yeah, and after you calculate the logits, again, now which are being influenced by theta and margin, you sort of return those instead of your regular logits from the classification level model and train on those. Sphere face. So sphere face sort of came before arc face, and it has a very similar implementation. The only difference is in how the mask works. So in arc face, the mask is, in a way, additive, but for sphere face, it's sort of different. The rest of the implementation is identical. It's only here in how you figure out how the margin mask works that would be different. You would have to go through the paper to understand what formula to use here, but rest of it would be identical. So yeah, once you all do fill in these two blocks, we've also provided you the train function itself. on how, which you can just copy paste into your main notebook when you want to do fine tuning, right? So we have this fine tune train, which we would like you to move over to your main notebook. Right, so that was arc phase and sphere phase, how to implement it. And then there is center loss. Center loss is a little different in how it works. As Arya mentioned the theory, I won't really cover that, but implementation-wise, it is quite different if you see even in structure compared to the others that we saw, where the others were taking in the model, there was margin, scalar. Center loss is much simpler to implement. It doesn't really have any of that. It works more like a auxiliary loss in addition to the cross entropy loss that we already have, and doesn't really take in the model as an input or try to modify the model itself, but only adds another dimension of losses, which indirectly influences how your classes are separated in the embedding and feature space. Right, so center loss, yeah. The arguments here are much simpler. There's no model, there's no margin, there's no scalar. There's just num classes and feed dims, which is like the embedding size again. And self-centers is the parameter that you're sort of learning here. In the other one, you had the linear layer parameters that you're learning. In this, the learned parameter is going to be self-centers, which are going to be the centers of each class. And what center loss tries to do is ensure that the distance between the class and the center of that class is as small as possible, and the centers of different classes are as far away as possible. So again, while training, this is sort of a good way of understanding if what you're doing is a contrastive loss, because the input's always going to be the image itself and the ground truth label, right? Yeah, so if we see here, this is sort of the distance that you will calculate here, and it would try to extract the loss out of that distance. So the implementation of center loss here itself is straightforward, but you need more steps and more changes in your main code to implement center loss. For example, in your main code, you would have to create this instance of the center loss itself, and you also would have to create another optimizer separately for center loss. So unlike the other two where you just have one optimizer, center loss does optimization in two steps, but parallelly. One that just optimizes the classification algorithm itself, and one that specifically optimizes the centers that we are trying to learn. So that is sort of something different that you will be using. Like till now, we've just been using one optimizer and updating just one. But if you want to implement center loss, you would be having two optimizers and updating them simultaneously. So we've also provided, we didn't really used to provide this code earlier, which used to make it quite tricky and challenging to figure out what exactly needs to be done. But we sort of felt like giving this to you all this time so that you can spend more time optimizing your networks and optimizing your other hyperparameters than just trying to figure out the code. So if you see here, this now takes the loader, and there are two optimizers. This would be an optimizer just like any other that you use currently, and then you would use the center loss optimizer as we've defined here. In addition to that, there is loss weight. So the way we had margin and scalar as hyperparameters for arc phase and sphere phase, we have a weight that is a hyperparameter for center loss. So now the rest of it is same, but the first difference that you can notice is here, where now we have two losses that are being calculated simultaneously and that are being added to get a total loss. So the first is the regular criterion, which could be cross entropy with label smoothing. And then this loss one is now your implementation of center loss, where we have the parameters of loss weight, and fine-tuning loss is basically the center loss class that we've defined, right? But this loss weight is the hyperparameter that, again, is something that you need to do ablations over, because if that is too small, then the influence of your center loss is going to be less. If it is too high, it could prevent your model from really learning, and it could disturb the distribution that you've already achieved through your pre-training, in a sense. So when we do fine-tuning, the two stages can be called as pre-training and fine-tuning. So yeah, if I refer to pre-training, it is all the training you've done till this stage. So we have loss 0, which is the regular loss. Then we have loss 1, which is the loss including the center loss weights. And then you just combine them. You update the fine-tuning losses parameters a little separately out here. And then this is the other big change, where you now have two optimizers being updated simultaneously, which is something different from what you might have seen till this point. Yeah, any questions about this section? It's a little strange, it's a lot, I understand, but just if anything that stood out in this? No. All right, yeah. And it's just us, guys. Feel free to say no also, it's okay. All right, so if once you all do finish finish sort of the code blocks here, whichever ones you choose, and you know your implementation is ready, we can sort of come back to the main notebook. And now I'll sort of go over how to integrate that code into your main fine-tuning pipeline, right? So you guys must be at this stage with the rest of the cells being blank. So in model definition, for example, let's choose arcface, right? Arcface for today's demonstration. So if you do decide to use arcface and you filled out the code and you want to implement that. So you'll copy the arcface block from this starter notebook, the fine-tuning starter notebook, and you will paste that in model definition, right? Yeah. Once that is done, you again recreate an instance of the model that you have used till now. You can check it. And then you reload the checkpoint from the pre-training stage. So both the processes don't need to happen in one go. You can do your pre-training separately. And once you've saved all your checkpoints from the pre-training, you can just come back to it later and do this afterwards as well. So all you need to do is whichever model worked for you, just for example, if you were using ResNet, and this doesn't really work, it's just a place filler code. But if you were to use ResNet, you sort of load your ResNet model again, and then load the checkpoint that you had saved. After that, we create an instance of the contrastive loss model. This example that I'm showing will only work for sphere face and arc face. That for center loss is a little different, but I think I sort of covered how to use it, and we can go over it if you all have doubts specific to center loss as well. So after creating an instance of the model that you used in pre-training, you create an instance of the arc face model. And as I covered in the init method for the class, we can see that the first argument itself is the model that you just loaded with all of its weights. You provide the embedding size, 700 again is a place filler. It will depend on what you've chosen for your architecture, margin and scale. This is sort of a good way to play around with it. So you could have a grid search where you keep changing the value of margin and scale and keep running this so that this keeps getting updated. So now that we have instantiated the model and the fine-tune model both, we can move on to just defining the loss optimizer in the scheduler. So we will have a fine-tune criterion, which will again be the cross-entropy loss here, because we are building on top of it. Fine-tune epochs. Okay, fine-tune epochs, right? You don't really have to fine-tune for too long. Your regular training could go up to 100, 150, 200 epochs. It's up to you guys, as long as you all are comfortable reaching the high cutoff. It's not necessary to train for 150 or 200. Maybe your model reaches it in 100. Good for you, right? But for fine-tuning, 5 to 10 epochs is good enough to get an understanding of whether it's actually working or not. And you should see improvements, at least in verification, from epoch 1 itself, right? Another thing to notice, the accuracies that get printed won't necessarily reflect the accuracy, test or val accuracy of your model itself, because of how we're sort of modifying the model itself. So don't really get worried if the train accuracy in fine-tuning seems very low or it doesn't update at all. It is the validation and test accuracies that are more important and are more reflective of how well your model has learned after fine-tuning, right? So that is just another thing to keep in mind. So fine-tune epochs, at least initially in your grid search, not more than 5 epochs. Once you've sort of settled down on something, at most 10 epochs. You shouldn't really need more than that. If you're using center loss, sure, you could use more, but for arc face and sphere face, you shouldn't really need more than that. Fine-tune optimizer and scheduler. So when using arc face or sphere face, these are going to be very similar to the things that you've used in pre-training as well. They won't be so for center loss. And once you've defined these, training function, we've defined the fine-tune train, so you can just copy-paste this from the other notebook as well, bring it here, one be as is, and then sort of the experiment section, right? The important things to remember is, when you do call the fine-tune train, to send in the fine-tune model and not just the model, make sure to send a fine-tune optimizer, fine-tune criterion, because if you're using the same notebook, it could probably, if the other variables are still in memory, it could possibly pass in the optimizer and the criterion from the early stage, from the pre-training. So it's important to sort of make sure that you're using the right variables for fine-tuning as well. And that is sort of pretty much how you would go about implementing ArcFace into your pipeline and do fine-tuning on it, right? Any questions about this? Okay. Any recommendations on optimizers for the two different tasks in general? If I assume they are different, understanding. Yeah. So we're not really optimizing for that long, so you could definitely experiment very easily and just figure out which one works. It's not as sensitive as it is, since you've already developed all your weights. So yeah, definitely. Thanks, Anand. Ablation study definitely works, but it wouldn't be as painful as it could have been for pre-training, because now you already have a lot of weights that have learned, and your model is already pretty good, right? So your update steps are going to be much smaller, and it isn't as sensitive. Yeah. Any other questions about implementing ArcFace or integrating or implementing fine-tuning in general? Yeah, if no questions, what do you guys think? Does this feel alien or does it feel intuitive at all? A little, yeah. But I guess if you do review this again, it'll probably make more sense. And once you actually do fine tuning, so our hope is you can sort of look at this video again, and then it'll feel much more familiar and intuitive, because yeah, this wasn't really covered in the earlier versions of this course, and it sort of becomes challenging to implement these without much help. So our intention is, yeah, even though we have so many people in the audience, everybody can still benefit from the videos as well, right? All right, so if you guys want, you can just open the starter notebook and try to look at the code and try to fill it in. We're here to help you to sort of explain what is to be done in these. It's a little tricky to do this over Zoom, so you guys can also try it and then post questions on the thread for homework too later. But yeah, that is sort of the hands-on component for today's lab, where if you guys want, you all can try to fill this in and see if it works. Try to re-implement it. If not, if you all still need to do work on your homework submission deadlines, on your deadline work, you all can work on that as well, and we could just have any other questions going forward. Yeah, anything else you guys want me to, anything else we should talk about or cover? Yeah. So just to provide some intuition about what margin and scalar actually do, they're not just two random words, but margin is sort of the delta that you want to achieve between two classes in terms of theta, since we are talking in terms of a hypersphere, and scalar is sort of the magnitude. This scalar is like it works for scale and it's a scalar multiplier, so it sort of works both ways, but it sort of increases the magnitudes of the classes that you want. So margin, the value of 0.5 looks really small, but it also depends on the number of classes you have, because if you have 7,000 or so classes as we do, using a higher value of margin could really lead to overfitting on the data that we already have, since we are really being very selective and we want a lot of separation between classes, right? Which is why it is important. And same for scalar. If you just have a very high value of scalar, sure, it would separate your training set very well, but it wouldn't generalize very well, right? Which is why even if you look at the distributions in the slides that Arya shared, it looks like, yeah, increasing it definitely works better. Why wouldn't you want your classes to be as wide as possible and the peaks to be as high as possible? But that is good only for if you just want to memorize the training set. But to generalize, we sort of need to balance a trade-off and achieve a mix of everything. So how has the homework 2 been till now? It's like the classification, verification, was it relatively straightforward to reach the early cutoffs? Yeah.
Make it into work.
Yeah. Right. Yeah, that's good. Yeah. Getting familiar and being okay with looking at figures and diagrams like this is sort of essential. So if this does feel alien, I intentionally want you all to look at it and keep staring at it to the point that you all don't feel odd because when you start looking at papers, yeah, we'll definitely be sharing this after the recitation. We were just working on it till now. So yeah, we'll definitely share it, Ankush. Yeah. And just other tips I would say regarding the homework. Of course, it's an intro class and you all haven't really done resonets or contexts. So spend some time, which is why this homework is one of the longest homeworks, where you have 3 more weeks almost from this point. So pace yourself properly. Spend, say, the first week actually trying to understand and getting familiar with going through the papers and literature for these models, because our aim is not just to cross the high cutoffs, but it's actually so that you all learn how to create these networks. Because some people do just copy paste code and they'll just run it. If they're unlucky, they'll get caught and then bad things happen. But some people pass through it, right? But that is not what we want to achieve, which is why we have 3 weeks. Spend the first week in trying to understand how fine tuning works, how to actually implement all of these, how to understand what these figures mean. And then you try to start implement them and run your basic initial tests, because there are a lot of things you could try, right? A lot of models you could try as well. We've sort of mentioned ResNet, SEResNet, and ConfNext in the documentation, but you could really try any architecture, maybe even newer architectures if you feel comfortable with that. These are just sort of the foundational fundamental ones that have really been very useful and are very popularly used even in industry and research projects. So being familiar with these is a good starting point. And yeah, definitely distribute tasks amongst the team, because it's not just the coding that you need to do, it's also then the ablation studies, which is another challenge, and then fine tuning, right? So yeah, that's sort of it, right?